Okay, so we move on to the next example, and in this example, we'd like to calculate an approximation to pi. Like the normal pi, that's the ratio between the area of a circle and its diameter, right? But we are going to do this in a kind of a very funny way. So let's consider playing darts. So our dartboard is a circle, and the dartboard is inside a square. So the radius of the circle is capital R, and of course, since the dartboard is exactly inside the square dimensions is 2R by 2R. Everybody happy with that? Now, all these little stars inside the dartboard represents throws that the player has thrown at the dartboard. Now, it's not totally realistic, because if it's a good player, one would expect a concentration of throws around the center of the dartboard, right? But so in this case, we assume we do not have a very good player, and in fact, the dart throws will be generated by a random number generator, and we'll get back to that in a moment, right? Now, how in the world is this going to help us to get an approximation of pi? The argument here is that if we can get a relationship between the area of the circle and the area of the square, and that relationship contains pi, we can actually get an approximation of pi by looking at the number of dart throws that are inside the circle and that are as opposed to inside the square. And this is now, of course, based on the fact that the dart throws are generated randomly. So it's assuming that we've got a random distribution of all the dart throws over the whole square. Right? And that's reasonable. So what we're looking for is a relationship between the areas, and we'll use that as an approximation for pi based on the assumption that if I have a uniform distribution of dart throws, I can look at the area ratio in terms of the number of dart throws inside each area. Okay, so let's just look at the area ratio. So actually it's calculated here. I don't know why the author decided to do this, but he actually looked only at a quarter of the square and of course a quarter of the circle. So he's saying the subscript C stands for circle, the subscript, well, it's not really a subscript. So AC is the area of the circle, AS is the area of the square, but he's looking at the quarter, so that's why he says that the area of a quarter circle is pi r squared divided by 4. Since pi r squared is the area of the whole circle, a quarter is pi r squared over 4. And the area of the square, but only a quarter, is of course 4r squared over 4. And so if I calculate this ratio, I get pi over 4. So the ratio of the areas of the circle, remember pi has got a value of 3.14. So it seems reasonable. The numerator is smaller than the denominator, and the area of the circle is in fact smaller than the area of the square. An easier way to get to this pi over 4 is simply to work with a full circle and a full square. So if it's a full circle, the area is pi r squared, and the area of the circle is simply 2r squared, which gives us 2r between brackets squared, which gives us a 4r squared, which gives us the same ratio, right? So I think you're convinced, I hope you're convinced that the area ratio is pi over 4. So this I've already mentioned really. We are going to take the number of darts inside the circle. Okay, let me rephrase this. We're going to take the ratio of the number of darts inside the circle to the number of darts inside the square as an approximation of a pi over 4. And of course, after the first dart, it will be a terrible answer. In fact, after the first dart, it will be 1, irrespective of where the dart falls. No, actually, it can be 1 or 0. If the dart falls inside the circle, it will be 1. If it falls outside the circle, it will be 0. So that's a terrible approximation. But as I increase the dart throws, I'll hopefully get an approximation that will get closer to the answer. Right, and so it means that we can calculate pi by approximation by calculating the ratio of the darts inside the circle to the darts inside the square multiplied by 4. So the outcomes of this exercise would be to break the problem down into smaller pieces, to identify what structures are needed to solve the problem, to correctly implement the nested structures, and then to, I don't know why it says different radius, but the point here is that we're going to generate the dart throws using a new function that we haven't seen before, numpy.random.uniform, AB. Okay, so let's talk about this numpy random.uniform, and of course, let me exit the full screen, and I've actually opened just a separate window, and I encourage you to do the same when you do your projects or when you do the test and the exam. If you want to get information about something or you want to try something, open just a blank window. How do I do that? Well, I, of course, go to this, like the File Explorer page, and I go to New, and I go to Python 3. That will create a Jupyter notebook with a name untitled. And it'll actually save it also there under that name. But so in the first cell here, I import numpy as np, and then I do a help np.random.uniform. This is the new command that we are now going to use. So let's see what it says if we do this. It says uniform ... method of empty rand. And okay, here's the important thing. Draw samples from a uniform distribution. But these samples are not integers. Previously we had randint. Randint generates integers in a uniform distribution. This function generates real numbers in a uniform distribution. It's not limited to integers, right? And you can see that the arguments is the low value, which is an integer here. Well, if you put 0, it will just read that as an integer. The high value is 1, but it doesn't need to be 1. This is just by way of an example. In fact, I assume that these are even default values. So if you don't specify them, they will use 0 and 1. Then the third argument is size. So here you can, if you want, instead of a single number, you can put an array, and we'll see that a little bit later on in this chapter. So here you can define the length of the array. And it doesn't need to be one-dimensional array. It can actually be a square array or a two-dimensional or three-dimensional array, in which case this size will be a tuple, giving the first dimension, then the second dimension, then the third dimension. The size in the first dimension, then the size in the second dimension, then the size in the third dimension, if you want a multi-dimensional array. But it's optional, you can leave it out. If you leave it out, it'll just generate a single number. Right. So what is a uniform distribution? A uniform distribution means that the chance is the same to get any number in that range. Statistically speaking, when I use this uniform, I can get any real number in the range that I specify. Now note also that it says here that it generates the uniform distribution over the half open interval, square bracket low, comma high, round bracket. That means that the low value is included, but the high value not. That's quite similar to randint. Except here now, with randint, you could just, the closest that you could get to the higher limit in the randint function is one integer value. And here you can actually get infinitely close to the upper value, but you can never get the upper value. Right? So it's actually it's a point that's not very important, and you'll therefore see that when the author of this program uses randint, he actually uses randint as if the highest value is also possible. Okay, we'll get back to that in a moment, but I think this explains what random does. And see if we then go back to our code. Let me go back to full screen. Let's then, so we've now explained what rand in uniform does. Okay, so let's think about our problem that we need to solve. What would be, to break it down into simpler steps, what would be the first thing that we would need to do? Anybody, just think about that a little bit. What would be the first thing that we'd need to do? We'd need to throw a dart, right? That would be the first thing that we'd need to do. And then, of course, later on we'll throw the dart repeatedly, but it makes sense to write a function around just throwing a dart once. And then we can do whatever calculations we need to do regarding throwing a dart once. And then we can later, when we want to throw many darts, we can call that function. Every time we throw a dart, we call that function. So certainly this is not the only way to address this problem, but it's a meaningful way to do this, and it helps us to break it down into smaller pieces. And even that is possible to do in different ways. I'm not claiming it's the only way to break the bigger problem down to smaller pieces, but it's a way of doing that. Okay, so how will we write a program that will throw a die? So what we'd like to have is that the die should be, a dart. The dart throw should be uniformly distributed over this area, right? The square area. How will we do that? Any suggestions? I've already given you a hint in telling you what function we're going to use, right? So, anybody? You seem to have an idea? Well, just offer it. It doesn't matter if it's wrong. Yeah. Well, okay, so what we'll do, we need to, of course, generate it from, I'm actually not sure what the code does, whether the code considers the origin as 0, or whether the code works from here to there, from 0 to 2R. Actually, it doesn't matter. You need to select that, and you can then do that. But so you're certainly on the right track. So one way would be to say, I want to generate a random number between 0 and 2R, or I can say I want to generate a random number between minus R and plus R. Right. Everybody happy with that? But that's not the whole story, though. What else do I need to do? Just think about this a little bit. I'm talking of areas here, right? So just calling a random number is like a one dimension, so I need a second dimension. Right? So I actually need to call this random function twice. One to get a horizontal coordinate of my die throw, and another, I need to call it again to get the vertical coordinate. So the combination of calling this function twice will actually give me the x and the y coordinates of a single throw. It's actually quite similar to what we did with a guessing game. There we had to throw a dice twice, and because of that, in the loop, we had two randins functions. One to calculate the one die, and the other one to calculate the second die. So here it's the same. We call the function twice. One to calculate or to determine the horizontal axis, so we can think of that as the x-axis coordinate, and a second time to get the vertical axis coordinate. And that's really all that our function that calculates a single die throw needs to do. So let's look at what we have here, what the author has done here. Right, so obviously he's using in record 5 and 6, okay, before I get there, of course he decided to call the function random underscore dart underscore position. It's just a name, you can call it anything, but that's what he has selected, and he's passing to his function just the radius of the circle, which is capital R in the example, right? And then this function just has two statements, record 5. which is using to calculate the x-coordinate of the die throw, the dart throw, my apologies, and record 6 that calculates the y-coordinate of the dart throw, right? But if we look at the way that he's using the function, we see that he's specifying minus radius to radius, which implies that he considers the origin right here in the middle of the circle. But it could equally well have worked if you considered the radius, the origin here, and for that matter, any other point. All right. The implication here is that of using it like this really means that you can actually throw a dart right on this border and right on this border because the minus r's are both included. But I can never get a dart that's exactly on this border and exactly on this border. That is because the rand, what is it called? The rand uniform function excludes the upper bound. But I think you can also from this conclude that it doesn't really matter here, because I can get infinitely close to the border on the right-hand side, even though I cannot ever get right on top of it. Okay, everybody happy with that? Right, so that's all that my random dart position function does. So that represents throwing a single dart. Okay, what else do we need to do? Right, so we want to, of course, repeatedly throw darts, and hopefully we'll get by counting how many darts is inside the circle and how many are outside the circle, we will generate an approximation to pi. So that probably implies something like a loop, right? I want to do it repeatedly. The moment I want to do something repeatedly, a good guess is always to use a loop. Sometimes, if I know how many times I want to do it, it will be a for loop, but when I use a for loop, I can perhaps also do it with an array instead of a for loop. But so to think in terms of a loop, whenever I need to do something repeatedly, is certainly not a bad way of thinking about computer programming. The important point is I need to decide if I want to use a loop, is going to be a for loop or a while loop. Now in this case, I think you should clearly see that it cannot be a for loop, because I want to throw I want to throw the darts until I get a good answer for pi. So I'm going to use a test. I'm going to use a condition. It will be basically on the accuracy of my calculation. So that implies a while loop, because I don't know how many times I'll have to throw the die. And it actually turns out, we'll see in a moment, that if I do this program repeatedly, because I'm using random numbers, in some cases I'll have to throw. I've actually played around with this morning. I had a case where I could get an accurate value for pi. I used the same accuracy every time. I actually could get a good approximation for pi with something like a 900 throws, less than 1,000. And I had a case where I had something like a 250,000 throws before I got to a correct answer. You never. So the point I'm trying to make is you cannot use a for loop, because you don't have any idea how many times you need to iterate to get to a good answer. Right. So that's the next thing that we'll have to do. We'll have to generate a while loop. We'll have to, in the while loop, call this function random dart position to represent a single dart throw. We'll have to count the number of times the dart is inside the circle, inside this square, and we'll then from that calculate the value for pi and then compare it to some other tolerance to see whether it's accurate enough. Once it's accurate enough, we'll exit the loop. Right, so this is then done with basically the function here, def pi underscore approx. I'll get back to that in a moment. The author here decided, and this is, I forgot about this, which is a good idea. He generated a separate function to check whether the dart was thrown inside or outside of the circle. And he called that function in underscore the underscore circle. He passes to this function, of course, so he's going to call this function every time he throws a dart. So the function function random dart position is executed once for every dart throw, and the in the circle function is also executed Of course, after the dart throw function is executed, this is executed to determine whether this dart throw was inside the circle or outside the circle. So he's passing to this function the x and y coordinates, which was really calculated by the random dart position function, as well as the radius of the circle. And he's given us, to tell us what he's doing, he's inserted in record 11 a comment here. This function will return the Boolean variable true if the dart is in the circle, else it's false. Right, so that's not too difficult. I can, with record 12, calculate the distance of the dart from the origin by simply using Pythagoras. I take the square root of the sum of the squares of the x and y coordinates, so that's what I'm doing in record 12. And then I return, between brackets, distance smaller than radius. Now you need to make sure that you understand this. If I have, of course, if I return, what I return is some other variable. And if distance is smaller than radius, it means that the dart is inside the circle, right? Because the distance from the origin to the dart is smaller than the radius of the circle. Then this that I've highlighted will evaluate to true. And it means here I'm returning true. And even though here in the function it's not really a variable, in the calling function, okay, depending on how I call this, it may actually define a Boolean variable that is true. On the other hand, if the distance is larger than the radius or equal to the radius, by the way, note here that if I throw the dart right on top of the circle, in this, the way that it's coded here, it considers that dart to be outside the circle because it's smaller than and not smaller or equal to, smaller than or equal to. But in any case, so when it's on the circle or outside the circle, this that's in gray here will evaluate to false, and so it will then return the false Boolean variable. Right, this function is then used to determine whether it's inside the circle. Now let's look at the main function. It's not the main program, like in the previous example of the, what is it called, guessing game, the previous example. We have three functions. We've got like a main function that calls the other two functions, and then we've got the main program that calls the main function. So the main function, if you want to think of it like this, by the way, the Python doesn't really think in terms of main functions and other functions, but of course it does realize that a certain function is called from another function, right? So what I'd like to call the main function is called then pi underscore approx, for the reason that this function will calculate an approximation to pi, and it takes two input variables, the radius of the circle and the tolerance within which you'd like to, the accuracy tolerance of that you're going to use to calculate pi, right? And we've already mentioned before that we're going to use a while loop, so you'll see that the whole function sort of revolves around a while loop, if I can find my mouse. The while loop is then from record 20 to record 26, what I've highlighted in gray now. So before it goes into the while loop, it initializes three variables it's going to use. And it makes sense that you'd like to count how many dart throws are inside the circle. So it defines a variable CNT for count. CNT, it's just a name, you can call it anything. Let me just check the time here. We have a little 9 minutes left. Okay, so the variable that he's going to use to count the number of dart throws inside the circle is CNT underscore circle, and then CNT underscore square is the number of dart throws inside the square. He's going to use the variable error in his condition to decide whether he should stay in the while loop or not, and because of that he initializes error to a value of 1. Which is a large number compared to the tolerance he's going to typically use. Of course, if you use a tolerance larger than 1, it will never enter the while loop and you'll get you will not even get an answer in that case, right? So that's just initializing the variables you want to use. Then in record 20, he enters the while loop, where he tests whether the error is larger than or equal to the tolerance. If true, and of course the first time around it will be true, it enters the while loop. In record 21, he then calls the random dart position function to represent a single dart throw, and he gets the x and y coordinates from that call to the function. Ladies and gentlemen, I just want to reiterate here that when you work with functions, in the calling functions, the output variables does not need to have the same names as in the function. You should remember that. We use it here with the same names because it's convenient. It will work like this, but you can also call it something else. And then also the radius, the variable that we pass to the function, we here use the same, I think it's the same, yeah, it's the same name, but it can also be a different name. Unless you use variable equals to value, then it must be the same name. Right, so record 21, I throw my dart. Then in record 22, I count the number of throws inside the, I increment the number of throws inside the square. Why do I do this? I don't test anything, I just add 1 to the number of throws in the square. Have you thought about that? Oh, you couldn't because you've never seen it before. But think about it now. Why do I simply say, well, irrespective of what the x or y coordinates is, I add 1 to the number of darts inside the square? Well, the reason for that is that any dart that's inside the circle is also inside the square, right? So it means that all throws need to be added to the number of throws inside the square. So that's why I can immediately, after I've thrown the dart, I can increment the number of darts inside the square. But that's not true for the circle. So because of that, I need to now call the function in the circle to determine whether that dart throw that I've now already added to the number of darts in the square is also inside the circle. And of course, so I pass to the in the circle function, the x and y coordinates and the radius. So that's how we constructed it. And I use this in an if statement. So if remember now, this in the circle function returns a Boolean variable, true or false. So if I get true, so note here, I shouldn't do this. Yeah, I should. All of this is a single call to the function. So what I have in gray here evaluates to either true or false, coming from the function. So if it's true, it means that the dart is inside the circle, then it executes an increment in the circle counting, the circle counter. But if it's false, in other words, the dart is outside the circle, it doesn't even go into this if construction, it simply jumps over it to record 25. Okay, everybody happy? Then in the record 25, I now calculate my pi approximation. Remember, the formula that I'm using is that pi is approximated by 4 times the number of darts inside the circle divided by the number of darts inside the square. Right, so that's exactly what I'm doing here. I'm saying the approximation is, and by the way, note that the approximation is calculated inside the while loop but outside the if construction, right? The approximation is 4 times the number of darts in the circle divided by the number of darts in the square. So that's my approximation. Now I want to, and this is the important thing for while loops, I must, inside the while loop, update my convergence, or my termination, the while loop termination condition. Otherwise, I'll sit in an infinite while loop, and if that happens to you in the test, it's a disaster. Well, maybe not a disaster, but you'll lose something like 15 to 20 minutes. So whenever you decide on doing something with a while loop in the test, try to do that as the last question and you answer that. So if this happens, you only lose the marks for the last question if you don't get everything restarted again. Right, so how do I update my while loop condition here? Well, I'm going to check what is the difference between the actual value of pi. Now, I know that. Well, I can calculate that from numpy. It's the np.pi function I'm using to calculate the accurate value for pi, and I'm going to subtract the approximation from that. Then I'm going to calculate the absolute value of this difference. and I'm going to say, well, this is my new error. So, of course, it means that if my approximation is close to the actual value, the error will be small. And hopefully, as I throw darts, I'll get, as I carry on. Remember now, the answer will hopefully get better and better as I carry on because of the fact that I've got more dart throws. The moment my error is then smaller than the tolerance in record 20, it will not again go into the while loop. It will jump over the while loop. It will then jump to record 27. That's the next executable statement after the while loop, which will then return to the calling program the approximation to pi and also the counter of the number of squares. Why do we return this? Let's see what they asked us. They asked us to where's the question? No, there wasn't a question. No, they never asked us a question, yeah. But okay, so the reason why we return the number of throws inside the square is that the number of throws inside the square is also the number of throws, right? So it's to tell the user how many times did he have to throw the dart before he got a good answer for pi. And so in record 30 then, I call my main function, pi approximation. I pass the radius of, in this case, 2. I think the problem statement didn't even tell us what the radius of the dart board is, but this can be 2 millimeters, or it can be 2 centimeters, or it can be 2 meters. That doesn't really matter. But the tolerance is then specified as 1 times 10 to the minus 6. So I'm trying here to get an approximation for pi that's better than 1 times 10 to the minus 6. Since pi is 3 point something, 3.14, we see that this tolerance is actually a reasonable value. It's probably quite close to the approximation for pi that you have on your pocket calculator. Maybe there the tolerance is 10 to the minus 8. Right, so after calling the main function, I'm going to print the approximation, and then in record 31, 32, I'll print the actual value of pi just to be able to compare it, not only through the tolerance, but just from the value. And then in record 33, I'm going to print the number of dart throws. And I suppose my 9 minutes is gone, just about. Right, so maybe we should try this function after the break. We'll have a break for 10 minutes. We'll reconvene at 12:30.